N3 space. Before we did intersection of lines into N3 space. Now we're going to do intersections of lines with planes. And then the last one is intersection with planes and planes. So if we have a line, which is here in green, with the purple, which is the plane, so it's any flat like paper space. If the line cuts right through the piece of paper, that's one point of intersection. You could also have infinite, which is where you have your plane, and your line will be lying right on your plane. And so you'd have infinite number of solutions there. And then this is what it would look like in that case. You'd get, when you're solving, you'd get 0t equals 0, and there's an infinite number of possibilities. So that's what it looks like algebraically. That's what it looks like graphically. And finally, you could also get where if I had a plane here and a line, those are parallel. Those would never meet. And algebraically, it would look like 0t equals 31, or 0t equals a number, where it's not possible to put in a t value that will make that true. Plane. So that's here, any point. P, that's just another point off of the plane. Q is any point on the plane. And then normal, you might be given an equation, or you'd have to solve for. So you take the magnitude of their dot product, and then you take the magnitude of that normal, and then divide them. Okay, so we are going to try to determine the point of intersection. And if you remember back to grade 10, if you were doing the intersection of two lines, you had different strategies. You had substitution and elimination. But ultimately, you're setting them equal so that you can try and find that point that they're the same at. You're trying to make them equal. Well, here in this plane, which just so you know, that pi symbol is just another way to call a plane. So it's not an angle, it's not degrees, it's not radians, it's a name. And then you have this line. So if you look at this first scalar equation, you have an x, a y, and a z. And then you look at your line. Do you know what x equals? Do you know what y equals? Do you know what z equals? So what can you do with those? Sub it in. We took the line equations, and we sub them back into the plane, the scalar equation. And now when you look at this new equation here, the only letter there is t. So can you solve for t? Yep, go ahead. So you get 0t equals 30. So with this is what being given, what does that mean in terms of our solution? How many solutions are there? That's right. So therefore, there is no solution, because there's no possible t that will multiply with 0 to get 31. You would get another example. You go through the same process, and it's just this that will look different. So it either equals 0, or you'd get it that you'd actually solve for t, and that you'd have an answer. And if you look at example 2 on page 476, there's another example where you're given different information. So you can take a look at that. So there's the second example. So if we're looking for the distance, we can write our distance formula, which is the normal dot the points. I'm going to make up another point B. Well, I could have said anything, but for now we're going to call it B. We don't know what B is yet, though. So if we need to know what n is, where can we find n from? From the equation, that's right. So the purple underlined spots, those coefficients are always the values of the normal. And sub in your point here. So this is just to check if A is on it. So you'd have 4 times 2 minus 2 times 2 plus 3 times 4 plus 1. And the right side is staying as is. And this equals 17. So is it on the plane? So once you've checked left side equals right side, since they do not equal, you know that it does not lie on the plane. And now you'll continue with this equation. B can be any point on the plane. So we can make any point up. So the way I'm going to do it is I'm going to figure out some sort of x, and I'm going to make my y equals 0, my z equals 0. I could have made x1 and then y2 and then solved for z. There just has to be one component that you've subbed into the equation so that that last component matches with your equation. But I'm going to make it easy, and I'm going to make the other two 0. So you solve for this. So if you solve, you have -1/4. So another point on the plane is as follows. And in our equation for distance, there's one thing that we need, and we don't have yet, and that's AB. Do we have A? Do we have B? Can we find AB then? Yeah, we take the b components minus the a component. So with AB, we go back to our equation here, and we want to do the dot product with the normal and AB. Well, we have our normal here, and we have AB here. So if we do the calculation of A dot AB, and remember, it's not just the dot product, it's the magnitude of it, so the length of it, meaning we'll always have a positive answer. And so do the x times the x, so negative 9 over 4 times the 4 is negative 9. Negative 2 times negative 2 plus 4. Negative 4 times 3 is minus 12. And the magnitude of that, and you end up with negative 17. But because you're taking the magnitude, you just take the 17. So the last part of the equation is finding the magnitude of the normal, and how do we do that? Now with the normal, you can actually just find the distance. It was the magnitude of the dot product, which is 17, over the magnitude of the normal, which is 29. And that is approximately 3.16 units.